I have Anna Filina talking about how to speed up your databases.
Thank you. So we only have 20 minutes, so I'm going to go a little fast. Speed matters. So what you need to figure out first is what is slow. So what's running slow, how to use indexes, how to choose them, how to write better queries, and I will provide you with a checklist at the end, which is not a full checklist. It's just a guideline, basically. So when you're designing databases and queries, and then it runs slow, so you can just go through this list and check whether you forgot anything. Yeah, and you can write indexes or indices. I know some grammar Nazis here might say, you have to say indices, but I find that when I say indexes, people associate it with an index much more quickly. So I'm going to use that word instead. Both are grammatically correct, by the way. So myself, I run a nonprofit conference in Montreal called Confu. It's a conference with Python, PHP, Ruby, Java, .NET, whatever. I also organize a PHP Quebec user group. So yeah, I'm a PHP person. I also do training and project rescue at FullLab, which is my company. And you can follow me on Twitter here, Filina. All right, that's out of the way. What is slow? So instead of telling you exactly what is wrong with queries, I will show you how to figure it out yourself. So you can do that when you work. One problem I found is when you have multitude of queries, often in loops. So ORMs tend to do that a lot. So you iterate over a result set, and you will query details, for example, when you display a table of results. So that is something you should avoid. So reduce the number of queries. You can check for lazy loading in your ORM. You can remove that and make sure that you actually craft your queries properly and return a set instead of going out and making, I don't know, maybe 25 extra queries for nothing. So always query a set. Well, this example is query pic details. I'm going to talk about albums and pictures as example of data. Another thing is you can have a lot of nesting. So for example, you would have a function getUser that will inside query something, the user. Then it will query call the getFirstAlbum function. It will query an album. Then it will query the first photo of the album, and then will query the thumbnail of that photo. So that's going to be four queries, when you could have probably done it in only one by saying getFirstThumb. So that's one trick. How do you count queries? When you do it manually, you're actually going to have to go and in front of every query, just increment a number that you can output later. With ORMs like SQL Alchemy, you can have listeners, so you can tap into that, and whenever you have a select, for example, you can increment a number, and there's also functions for that you can just extract the number. It can automatically do that for you. So you have to count how many queries you have per request. You can very quickly exceed hundreds of requests per page when you're not being careful. So no matter how fast each individual query is, if you have too many of them, it's not going to work well. Slow query log. So the examples I will give are mostly for MySQL, but you can also do a lot of that for Postgres and whatever else you're using. So in MySQL, you have a slow query log. So what you can do is open a file, a configuration file called my.cnf, and you can enable the slow query log, and you will define the threshold of what is considered to be slow. So you could say, for example, 2 seconds is too slow. So whenever a query takes more than 2 seconds to execute, please log it into this file. And then you can open that file and analyze those queries and try to figure out why they're slow. All right. So here's an example of schema. So I did a little benchmarking with fictive data. So I created a user table, an album table, and a picture table, and I linked them with foreign keys as such. I inserted 200 users. I inserted 100 albums for every user, and then 100 pictures for every album, for a total of 2 million pictures in the table. So it's just a loop that inserted a whole bunch of stuff in the database, so I could see how fast queries would run. So a simple query with a join, because that's where the trouble occurs when you use joins. I would select a ID and title of a picture. So I want all pictures from user number 1. So I would go about starting with the picture, then left join on the album, and then I make sure that the album belongs to user ID 1. So that's a very simple query. With that data set on my machine, it took 38 seconds average. So that's without the cache. First time, it's going to be 38 seconds. But obviously, every time you modify any of the data in any of the tables, the cache invalidates, and you are going to have a 38-second database query. So that doesn't even count all of your bootstrapping your framework, for example. So that's really crazy. So while it fetches the pictures, I have time to do a space jump. By the way, that was awesome, right? All right, I watched it live. It was unreal. So why is it slow? So once you find that query that takes 38 seconds, which is amazing, so why is it slow? In MySQL and also Postgres, you can use explain. So you take your query and you prefix it with explain, and then you get this big table down there. I will just expand that and show you the details. So basically, every row corresponded to a table in a join. So you're joining on two tables, so you're going to have two rows with details. So it's going to query in the album. It's not going to use any key because you don't have any indexes in your database. And it's going to scan 20,000 rows because that's how many albums we have for all our users. It's going to scan also 2 million picture records. But the problem here is because you're doing a join, it's actually 20,000 multiplied by 2 million. So it is 40 billion rows that you are scanning. So the metaphor for indexes for people who are not familiar with them, because everybody says we should use them, and I still find people who are not using them. So it's like when you flip through an address book. If you're searching for a name just randomly there, just scanning everything, it can take a while. Instead, you can pull on a tab with a letter. For example, if you know that the name is Bob, you're going to pull on the B tab, and you can get to your result much more quickly. So we add an index. We do an alter table. We add an index on album.id, and that will reduce the query. The same query we had is going to execute in 2.38 seconds. So you just save 36 seconds on every request, but it's still quite slow. Under the hood, what happened is that it could find the album right away because it only had to scan one row because you had an index. So it's like album.id, it fetches that album, and then it scans 2 million picture records. So that's a lot less rows that you need to scan. We can go further, and we can add an index on album ID in the picture table. So that's when we join the two tables, you are joining on album ID in the picture, because you need to know that the picture belongs to the album that belongs to that user. So now this query is down to 0.12 seconds, which is already 300 times faster than the original. And what happens under the hood is that we still need to scan the entire album because it only is going to use one index on each side. For example, when you have a join and you have indexes on both columns, it's only going to pick one of them, the best one. So it doesn't use an index on album, but it does use on picture. So picture.albumid is used. So it's 20,000 rows times 100 rows, so it's a lot less rows scanned. Oh, already, that's fast. All right, so we're adding the last index on user ID, and now we're down to 0.10 seconds. It doesn't look like much, but it is a 70% speed gain. Under the hood, 100 on one side, 100 on the other. So with the second index, we're only scanning 100 pictures for a total of 10,000 rows. All right, so we can see that the indexes that contributed the most to our performance are foreign keys. So primary and foreign keys make for great indexes. So whenever you have a join, see on what you are joining and try to add an index on that. Whenever you use a where, so for example, if you say where album user ID equals 1, so you would want to add an index on that. So whatever you're using to filter out your records the most, make for best index candidates. do we need to optimize further because we're quite fast already? But when you go through airports custom, if you have like 5 custom officers and 1 minute to process a traveler, if you have only 5 travelers per minute, it's fluid. It just keeps going. If you have 20, then you have a queue that slowly builds. And with 1,000 travelers, it's a 3-hour wait if you arrive on the 2nd minute and a 6-hour wait if you arrive on the 3rd minute. So you would probably just shoot yourself rather than go through customs. And this is synonymous to your users actually leaving the website because they come in and there aren't enough database connections to process all this traffic. So this is why you need to process each request as quickly as possible. And this is why you only connect to the database when you need it, and you disconnect when you don't need it. So even microseconds matter. So it's either the ever-growing queues, or you just ride on a highway at full speed. This is the first situation is not where you want to be. So some more tips: you can use smaller indexes. Big int is slower than tiny int. Also use unsigned because you can double how many numbers you can squeeze out of a tiny int, for example. So because when it's signed, you use the negative numbers, but your index is probably not a negative. So user ID probably starts at 1, so you don't need anything below 0. So you just make it an unsigned and you can squeeze a lot out of it. Tips for some better queries. When you use indexes on a column, don't use functions on those columns in the where, because although you can access the index directly, once you use a function, it's a different value that you get out of it, so it cannot access it directly, and it's going to scan the entire table. So for example, if I want everything that was uploaded in 2011, it's going to be a problem. So it's going to take much more time. It will simply not use the index, and you can get back to 38 seconds of fetching. So, you know, when you pick up firewood, as soon as your hands are full, you don't care about the other firewood lying around. So you can just limit the number of results because you are probably not going to display 2 million pictures in one page. So you would limit the number of results. So basically use pagination. And this is down to 0.009 seconds, which is 100 times faster than our previous 0.10 query. You can use other constraints to fetch less results. This is not as fast as the other one because we're using picture.id, but you can say between. I'm not sure if it's the same in Postgres. So you can say between. It only makes sense if that column has an index on it once again. So always think in terms of indexes. You can use an in clause as well. So only fetch the pictures that you care about. You can split tables. The MySQL can partition your tables transparently. So you can say, okay, this will be a partitioned table. So when you get results from it, it's as if it was one single table, but in the background, it's actually creating separate files on disk. So it can make things a lot simpler. Also, don't underestimate archive tables. The MySQL has an archive storage engine. So it doesn't support update or delete, but it's very fast for selects. The only downside is that it has to scan the entire table. So only use that for data that you need to pull out of archives, like for logs and whatever. So you can use that for transaction use, whatever you don't need to pull on a daily basis, because you cannot have an index in that. But it's very fast because it doesn't allow update delete. It compresses the file on disk as well. So that's pretty cool. And you can also split database. It's also called horizontal partitioning or sharding. You can create different databases. For example, users 1 through 1000 will be in the first database and all their pictures. Users 1001 through 2000 will be on the second database. So that way you can even out the load. And you have tools in SQL Alchemy, I think, that allows you to do that automatically. So it can handle it for you. Yes. So the checklist, we're almost done. It's very short, 20 minutes. So the checklist is count your queries. Make sure you don't have too many of them. Log the slow ones. Use explain and check how many rows you are scanning. There are other things you can see, like index candidates, indexes that weren't used. Try different indexes and remove the unused ones. So if you see that you created an index, but it's never used in any of your queries, it is probably slowing down your queries, or rather the updates. Use small indexes, preferably numeric. If you use strings, it's still going to work for short strings, but as you get to bigger strings, it's going to get slower. Don't avoid functions on the index columns. Limit the number of results and try to split tables and databases when you have tried all the other options. Okay, and further reading, you can read about SQL Alchemy profiling, something about storage engine. So that's specific to MySQL, but you will find some equivalents in other databases, and a blog post about charting as well. So yeah, do you have any questions?
We had a script that was malfunctioning, and it was silently failing, but the way it failed was that it injected a whole bunch of garbage data into our database. And we spent like a day trying to profile this thing to figure out where the slow query was, but it turned out that the actual data was messed up. So
right.
That's another place to look if you're having trouble debugging one of your queries.
Yeah, I mean, you start with this checklist, you see, okay, I've tried this, so once you've ran out of solutions, then you have to dig deeper and find other profiling tools, because it might be in your code, might be in corrupted data, whatever. Thanks for sharing.
So I have more of a curiosity kind of question. So we had a Postgres database. We were trying to get, we had a table with an index on date, and we were trying to get all the values for today. And so we ran a query using where day is equal to now, the function. And we found there was a huge optimization lift if we replaced the now with an actual hard-coded string.
Yes.
And I'm just curious, like, why, like, how does that get evaluated? Like, why is that such a big difference?
Okay, so what happens is that because now is, like, every second, basically now is a different value. So when your query runs, it actually gets cached. So as long as your data in the tables has not changed, it's going to fetch the same result again. So it doesn't go through the through all the records. When you use something as dynamic as now, you obviously cannot cache anything, because every second your cache gets invalidated. And this is why you need some values, like by the minute, depending how long you want to keep your results in the cache. If you're fetching something live data, then you might want to have a 5-second cache. If you're fetching news articles, then maybe 5 minutes would make more sense. You're welcome. All right, I guess it's coffee time.